Yeah, on behalf of Space Education and Research Foundation, and on my personal behalf, I am very happy to welcome Professor R. Suresh and all the participants who are joined this webinar on satellite meteorology. This webinar will have 5 talks, and today is the second talk, which is going to be operational and research and development of meteorological satellites. Though yesterday I had introduced Professor Suresh, but as a custom, I will once again welcome him and say a few words about him before I request him to start the talk. Professor Suresh had a very excellent academic career and have contributed to meteorology and satellite meteorology to a very great extent. And his work has been recognized by several awards that he has received. And he still continues to give classes and teach in universities, colleges, institutions, training centers, etc. And he's an excellent teacher. Yesterday, I think all of you will agree that yesterday we had an excellent talk. There were slight interruptions because of internet, which we can't help it, but he made the subject very clear, and wherever there were slight internet problem, he stopped and started the talk from wherever it has originally stopped. So it was more or less continuous. I heard the talk yesterday, which is recorded, and these talks have been put on the internet, and the links are available on the website of Space Education and Research Foundation. Many of you must have seen this by now. So, and currently, Professor Suresh is a chairman of India Meteorology Society, Chennai chapter. So with these few words, I now request Professor Suresh to start his talk, and I will close my video and audio and continue listening him as all of you are doing. Professor Suresh, please.
Thank you, Professor Butts. Good morning, good afternoon, as applicable to the international viewers. Today's module, as Professor Butts was mentioning, it is operational and R&D meteorological satellites. By operational, we mean it is used in the day-to-day forecasting purposes, monitoring purposes, and other things. R&D means without R&D, the operational thing will not evolve. So R&D, research and development, is a must in any field. So is the case in remote sensing application. We have come through a long way from 1957 or so, and first experiment started sometime 15, if I am right. I'll be covering those aspects in today's topic. In yesterday's module, we covered or we discussed the basic radiation physics which governs the remote sensing technology which is being used in our satellite meteorology. In yesterday's module, we deduced an equation for the orbital period by means of which we will be estimating the polar orbiter orbital velocity and the height of geostationary satellites, because geostationary satellite will be orbiting at the same rate as that of Earth. Now, today's module, we are going to see how the R&D satellites have evolved and how the operational satellites are being improved over decades, and the payloads which have been used in both polar orbiter and geostationary, and what are all the applications. As a preamble, I have to cover something, then alone I will go to the topic. In yesterday's lecture, I have not discussed about the swath width. I kept it purposely only for this. The swath width is almost meaningfully conceived as, students of astronomy will very well know, there is some term called a dip and declination in astronomy. In the day-to-day life, if we climb up and up over some building or mountain or something, we will be in a position to see the visible horizon wide. As we go up, the horizon will be wide. Our viewing angle will be large. That way we will be covering much. Same concept, when the satellite is above the Earth's surface and located at a height, its viewing distance, in short, can be considered as swath width. When a satellite is passing over, especially the polar orbiter, exactly down below it is called a sub-satellite point. From that point on either side, depending on the angle at which the radiometers, the camera, etc. will be having the field of view, the total field of view, the total coverage on either side of the sub-satellite point, the total distance is called as swath width. In other words, it is farthest range on the surface that can be viewed by the scanning radiometer on board is the swath width. You can see in the graph I have given in a pictorial form. This is the Earth surface. Satellite is mounted over here, and the satellite is looking at up to a portion alone it can go. It will not view here, so it can limit its surface maybe here depending on the altitude. It will be reduced like this. At a particular height, I have drawn like this. The angle WC is the viewing angle, or otherwise it is called as look angle. Viewing angle or look angle, interchangeably it can be used. And pi c is the angle which the look angle subtends with a vertical. Beta is up to what distance the satellite will be covering that particular angle. Everything has been put. Now we can apply our spherical trigonometry. Same graph I have for understanding purpose. Sin beta by the total distance, that is radius of Earth plus altitude of the satellite, r plus h. H is the altitude of satellite, capital R is the radius of the Earth. Sin beta by r plus h is equal to sin WC by r. Now we know r, we also know h because we are only launching it. What is unknown is WC and beta and pi c. So this can be deduced from this particular equation because all the three angles put together is 180 degrees as normal trigonometry. R is known, H is known, and this denominator both are known. If I keep my WC as fixed, say for instance 45 degree of the satellite look angle, this also we can only decide. So by substituting the 45 degree for WC and the satellite height or altitude we know, I have to say altitude technically, the satellite altitude is known and viewing angle we are fixing it. So if I substitute in this particular first equation, then I am getting the swath at one direction, then we are multiplying by 2 so that both the direction will be covered. That is why I am giving swath is twice this distance. For a lower height, instead of 1387 km, the swath width is 3208 km. For a lower height of 740 km, the swath width will be 1552. That's what I was saying in astronomy. The visible horizon will be depressed once the viewing angle is lower and lower coming to the surface. And once we go up and up, once the viewing angle is smaller, then the swath width will be higher. For viewing angle of 81.3 degrees Celsius, 3 degrees, And for a geostationary orbital height of 35841, the SWAT can be as high as 9,000 kilometers. So the geostationary satellites will be having a higher view as we naturally expect because it is at a higher altitude. One more thing we have to know before proceeding into today's class. There are three important velocities in satellite meteorology we are supposed to know. 7.9 kilometer per second, 11.2 kilometer per second, 16.7 kilometer per second. The 7.9 kilometer per second is called as the circular velocity, so that particular satellite will be revolving around, say for example, around the planet Earth in a circular orbit. So that is the velocity. That is why its name is called as circular velocity. The minimum velocity required to move away from the Earth attraction, pulling power, etc. But still it will be in the same solar constellation, solar orbital system. That velocity, when is exceeding 11.2 kilometer per second, is called as the escape velocity. That is, it is escaping from the Earth. It will not fall back to Earth. That is the meaning. Once the velocity exceeds 16.7 kilometer per second, whatever be the satellite or projectile we are releasing it, it will escape beyond the Earth atmosphere complete system, and it will leave the solar system also. In short, circular velocity is 7.9. Anything between 7.9 and 11.2, it will be projecting in a elliptical path, and it is still not leaving the solar system. The moment it is away from the Earth's surface, it is 11.2 and 16.7. It is still in the solar system. The moment it exceeds 16.7, it leaves the solar system. There are two synchronous satellites. One is sun synchronous, another one is geosynchronous. We will be covering now. The sun synchronous orbits, which normally we used to call as polar orbiting satellites, because it is orbiting from pole to pole. It covers from north pole to south pole to north pole, continuously going on. For a sun synchronous orbit, the inclination angle as per the astronomical elliptical path geometry, inclination angle should be 98.8 degree for a semi-major axis of 7228 kilometer, and it has an eccentricity of 0. What is the advantage of sun synchronous satellite? It has the equator crossing times same or fixed. Say for instance, if it crosses over a particular flat launch, say Chennai or Delhi or Mumbai or some other place like in the tropical region, whatever you call, because we are discussing more on upper countries. In case it crosses at the local time of, say for instance, 9:42, in all possibilities, tomorrow also it will cross the same location by the same time. So that is the advantage of sun synchronous. It is synchronize the motion with that of sun, so that the rising and then setting of sun coincides with that of the polar orbiter. We have introduced two notations. One is the morning satellite. The satellite, once it is assigned the local time between 6 and 12 hours, is called a morning satellite, and it has to descend. The moment it is ascending, it has to descend also. It will descend sometime between 18 and 24 hours local time. So this is the definition for morning satellite. The Sun synchronous satellites will be having almost near polar orbits. That's what we started with. This view graph, the path of Sun synchronous satellite, it starts around 3 hours local time. It goes like this, goes to the North Pole, comes back, it is descending, it is crossing over here, then it is coming to the Southern hemisphere, goes out. Again it is from 3, it has ended up somewhere here around 4:15 or so. Again it starts 4:30. You can see that equator crossing time 3 o'clock here, and the next area which is separated by more than some thousands of kilometers at 4:45. You can see the timings. 3 o'clock local time, 4:45 local time, 6:30 local time, and 8 hours local time. You can very well see that what is the time difference. It is 1 hour and 45 minutes, 105 minutes orbital period. That is what we have deduced in the first session. So it revolves completely. It has an orbit rotation covering the North Pole to South Pole. This is the geometry. After this, for a particular satellite which goes on, the paths are going. It may be confusing initially, but I will be explaining in such a way that you will not be getting any problem in understanding it. Wherever these lines are there, that particular area is covered by the satellite. Once these lines are covered by the satellite once, and the hatched area is covered more than twice. See, just to follow the path between two consecutive parallel lines, the satellite will be having the swell. So same area will be repeatedly covered. The same area will be repeatedly covered in the hatched line, that is both solidus and then reverse solidus. You can very well see that there is a white portion in between, a coverage of once, a coverage of more than twice. What is this? That particular area will not be covered by this particular satellite at a time. What does it mean? We want a satellite to cover total globe, but there are some packets which are uncovered. So for that, we have to increase the number of satellites. It was calculated that if we have 8 polar orbiters, so this set of parts can be totally nullified. So this particular view graph is given a name called space-time sampling. The low Earth orbit polar orbiter satellites, they have the limitation like this. There are some packets of Earth between two successive satellites of the same satellite will be totally missed. On the contrary, geostationary satellites will be continuously monitoring the same area frequently, periodically, consistently, continuously. All the languages I can put. Only thing, the other side of the globe, probably geostationary satellite will not be in a position to cover. That is why I am saying that the geostationary satellite will cover almost 42% of the globe once it is placed over a particular longitude over the equator. Now coming to the actual topic of today's lecture, evolution of satellites. The very first idea came sometime in 1955 and was put into actual implementation sometime in 1957, October 57 4th. The first satellite by name called Sputnik 1 was launched by USSR. Sputnik 2 immediately within a month or so they launched, and then they wanted to see whether any living being can be sent. A fortunate enough living being called Laika, a dog, was sent. And thereafter, the satellite was continuously going on, and then the evolution started much a bigger way. The Americans started with the Explorer, Vanguard. Now the very first idea of making a sensor, which is again a passive sensor, which detects only the uplink radiation. Active sensor is one which is similar to lidar or radar. It emits a pulse and then receives it. Whereas the passive sensor is nothing but it receives only the uplink radiation. It will not transmit. So the very first radiometer, a passive radiometer, was devised by two doyens. One is called even the father of satellite meteorology, Professor V.E. Suomi, and University of Wisconsin is pioneer, especially in satellite sounding retrievals, Professor R.J. Parent. They collaborated and then they first conceived the idea and then put it into operational use on Explorer 7 satellite, which was launched on 13th October 1959. From that period onwards, the meteorological satellites started coming into almost like a mushrooming way of thing. So many satellites. The current day, I cannot even think of how many are right on orbit. The first satellite, TESS one, that is Television Infrared Observation Satellite. It was launched by US on 1st April 1960. This is considered the earlier one, whatever Suomi and other they tried, that was on experimental basis, and then with that operational satellite started with TIRAS 1. From 1950 to 1965, as many as 10 TIRAS satellites were on orbit. They carry the payload of Super Vidicon camera, which is nothing but an improved version of the erstwhile analog camera in those days. So current day we are having so much amount of megapixels. So at that time it was not that high. Even then it was a digital camera, Super Vidicon camera. And in addition it carried passive infrared radiometers for sensing the atmosphere both day and night. And the first transmission started with something called automatic picture transmission, APT, onboard satellites on TIRAS 8. It was having a very coarse resolution, maybe around 27 kilometers. So I have seen that paper long back. APT pictures that used to be recorded in a ground station with thermal paper, etc. Probably it will go bad after some time because of atmospheric moisture contamination and other thing. But nonetheless, the picture transmission started long back in late 1960s. Then the Environmental Space Science Services Administration, ESA, started launching a series of satellites, ESA 1 to ESA 9. Contemporarily, National Aeronautics and Space Administration, which we used to call as NASA, they launched a series of satellites by name called Nimbus 1 to 7. So in the Nimbus 1 to 7, a variety of instrumentation was on board or loaded, and then with that, some profiles have been obtained, ground validated, improved the sensor capability, processing capability, this, that, all. It was like chain of event which was taking place. And with the success of Nimbus, the idea of Landsat program started by many countries. The first naming of satellite by NASA, that NOAA series, NOAA 1, was on 11th November 1970. And it was having only Vidicon camera. In NOAA 2, the Vidicon camera has been replaced by multi-channel high-resolution radiometers. We are called very high-resolution radiometer, VHRR. The current day we used to say AVHRR. And even recent time, still some more nomenclature has changed. So the VHRR was on board in NOAA 2 in 1972. The Nimbus 5 instrumentation was having ITPRR, that is infrared temperature profile radiometer, which is nothing but the sounder. which is similar to or complementing our radio sound techniques. So it gives the vertical profile of temperature. So the very first vertical temperature profile was started received from Nimbus 5 way back in 1972. Then the VHRR has been improved by a version called AVHRR, Advanced Very High Resolution Radiometer, on board the TIRA's N series from 1978. The characteristics of AVHRR, they have been tabulated in this particular table. There are two visible channels, though the second visible channel is just crossing the 1 micrometer, which is the IR termination. But yet it started from 0.72 micrometer. That is why it still called as it was still called as visible band. 0.58 to 0.68 visible band was used for cloud mapping. The cloud pictures will be very crystal clear. I will be showing some pictures in this lecture or in lectures. The second visible band was used for surface water boundary delineation, and water vapor correction was used in the near IR band of 3.55, 3.93 microns. And there are two atmospheric window channels, 10.3, 11.3 micron, and then 11.5, 12.5 micron, which are for thermal mapping as well as water vapor correction. In addition, the sea surface temperature also started by these satellites. Estimation of sea surface temperature based on the micrometer radiation upheld and then received by the satellite and processed with the devised algorithms. The high resolution infrared radiation sounder, which is acronymed as HIRS, they carry two bands. Even now also these two bands are very much active, 4.3 micron and 15 micron region. One will work in cold condition, other will work in warm condition. So with that, the temperature profile, etc., in sounding performance, everything was intact, and then we got a good values also. Now, the HIRS experiments successfully, whatever has been carried forward, 1970 to 77. So that has showed an improved capacity, and further later on, there is something called TIRAS Operational Vertical Sounder, TOVS module started being in. That carries, in addition to HIRS, something on micro sounding unit, something on stratospheric sounding unit put together. So that came to being after 80s. So as I said, TOVS, TIRAS Operational Vertical Sounder, on board October 78. People started using it continuously throughout the world sometime in 1980s. So much amount of validation has come in, and with the what you call a substitute for the ground-based radioson radio wind technique, and the radioson information can be derived from satellites, maybe at a finer resolution than what the ground radioson station provides. Because as of now, the ground radioson stations are sparsely located. Maybe one in 250 kilometers, 300 kilometers, 450 kilometers, sometimes very close also, but they are not equidistant. Whereas in the case of satellite, which is viewing the total area of viewing alike, so the resolution are two successive sounding points. The data between two successive points is very much lower than that of what the existing radio station, which are sparsely located, provides. So that is the advantage of TOVS. It comprises of three payloads: HIRS, which has 20 channels, out of which 19 channels are IR, one channel is visible, and microwave sounding unit, 4 channels, stratospheric sounding unit, 3 channels. Nice description and a textbook like of proceedings have been compiled by Rao et al. 1990. The reference I have given at the end. Interested viewers can view from the free access available or from any of the library. The characteristics which may be difficult for you to view, but anyway I will explain. Out of 20 channels, what I have rounded here is the channel number 20, which is invisible band. That is for the cloud mapping, cloud detection. 50 micron channels will work on cloud region or very cool surfaces. 4.3 channel work on warm region, temperature, retrieval. The microwave sounding unit and stratospheric sounding unit, they carried 4 channels and 3 channels respectively. They are useful for deriving the atmospheric temperature at the millibaric pressure stated herein. 700 hectopascal, 300 hectopascal, 90 hectopascal by the MSU, microwave sounding unit, and 15 hectopascal, 4 hectopascal, 1.5 hectopascal, which is the stratospheric level by SSU. Some of the channel characteristics of TAUs have been given over here. Yesterday we have seen what are the atmospheric trace gases which are specific to particular wavelength. That has been put over here. That is the purpose for that particular slide. The technical details of AVHRR TAU system components that has been listed over here. Field of view is nothing but the resolution. For the image resolution, which is of far lower than this one, that is 1.3 milliradian, which corresponds to 1.1 kilometer. This is the image channel. For sound resolution, it starts right from 31 kilometer. It ends up with 187 kilometer. That is what I said. It is far better than the existing coarse resolution radiometers, radio sound stations at the ground level. Onboard craft, what are the sensors available? That is only for academic interest, and then in the PDF, the viewer can view it if not already done it. Now coming to the SAT, the satellite passes along with the resolution of a polar orbiter. Once it is traveling from extratropical latitude towards the poleward side, that you can see the projector how it is. This is the poleward side. There is an area right over here. So the satellite passes have common. That is what in the space-time sampling we have given a hashed line of viewing the same area more than twice. What it suggests is that the polar orbiter has a continuous coverage towards the poleward side. That is why it always covers the area of interest over the extratropical latitude and near pole, and then that is useful for nowcasting purposes over the extratropical and polar latitude. I am seeing somebody else, the mouse also coming in, that is why it is getting altered. So I am coming to the same slide. This software has its own limited application, I feel. Some of the viewers' names are coming in, and then the moment the names are coming in, is going to the slides. Viewers, kindly don't keep on your mouse on the screen, please. Yeah. So we left over here. This is the last slide we discussed. So polar side, it is covering very nicely, and then that is one of the reason probably the polar orbiter satellites are useful for nowcasting over the extratropical and poleward latitude area. The scan geometry of the TOVS, especially the resolution part, over the sub-satellite point, which at the center line we have given. Even I am not going to move my mouse so that it won't be disturbed. Over the sub-satellite point, the resolution will be very fine. HIRS has a resolution of 17.4 kilometer. When the satellite is just over the particular station, maybe at every 20 kilometer or so, you will be getting a vertical profile, which cannot be thought of by the ground-based radio sound. As far away, this particular HIRS sensor has a resolution of 58.5 kilometer that has been described over here in this particular view graph. Whereas the MSU over the subsatellite point, it has a resolution of 113 kilometer. At the end, it ends up with 323 kilometer. It all depends on the field of view. Field of view is nothing but the resolution. In this case, the HIRS resolution, which we have seen earlier, is compared with the SSU. It starts with a resolution of the satellite point of 147 and ends up with 244 kilometer at the edge of the scan over the swath. Now coming to the picture, because our topic of today is how satellite meteorology evolved. That is, even legacy pictures I am supposed to show, and then how best it was and how we have come far away from that particular group, and then still now also that is giving a good clarity according to me. Two cyclones at the same point. You know the location. It's over US. It's Eastern Pacific. Hurricane Lone on the left hand side, Hurricane Christian on the right hand side on 24 August 1974. You will be able to see the center dot, which is nothing but the eye of the storm, and the streamers which are coming far away from the eye of the storm and then merging, whirling over the center of the point, and then thereby the eye wall is getting formed, and then complete fury of cyclone has been put over there. And the streamers at one particular point, they are having almost like a conjoint. Each one is having almost like a cooperative mechanism. One field band, another band, probably the thing which is segregate these two. From that advantage of whatever we derived from TOVS, the technology has evolved advanced TOVS. It carried, in addition to improved HIRS, improved AMSU, that is Advanced Micro Sounding Unit. It is having two branches of advanced AMSU, AMSU A and AMSU B. One is having 15 channel, another one is having 5 channel, total 20 channels, in comparison to TOWS, which was having hardly 4 channels. And the significant improvement was in TOVS temperature retrieval, depending on the mid-troposphere or top of the troposphere. It varied somewhere between 2 and 4 degrees during that period, different phases of whatever experimentation they have done. Now with ATOWS, it has come down to less than 2 degrees Celsius bias, which is nothing but the error between the satellite derived temperature and the co-located radiosonde profile. By co-located, exactly at the same time of radiosonde release, the satellite will not pass over. We considered plus minus 1 hour, plus minus 100 kilometer as the validation point. The validation criteria may change depending on the researcher whomsoever did it. This is by and large an acceptable version. In addition to the temperature profile, dew point, and then GPM height estimation from the ATOWS, we used to derive or infer using our dynamic meteorological concepts, thermodynamics, the total precipitable water and liquid water current, rain rate, snowfall. Viewers, as I said, the resolution part also started improving. The moment we have the radiometers having the field of view very fine and fine, the resolution started much improved. So the AMSU resolution started coming to 48-kilometer spot at every location. We will be in a position to get the critical temperature profile. Always I was giving a success story of satellite technology. I am just give you what is the caution. Though I mentioned this in space-time sampling. There I mentioned two consecutive satellite passes and then how they are covering as a single line as hash or more than single line as a solidus and then more than one satellite coverage as hash. There is a small white portion which left uncovered. Over the white portion, exactly, the hurricane Mitch was located between two consecutive passes of the satellite. This particular cyclone was totally hiding itself, was unable to be detected. It's a classical picture which you can see in the internet world nowadays. It should be available. This I am having in my kitty right from 1990s. So the hurricane Mitch was missed, and then this is the problem not with the satellite, it is a problem with the geometry. Probably the next satellite may take covered it. By the same satellite between two consecutive satellites, depending on diamond of the cyclone. So if the cyclone is small, definitely say between two consecutive passes, and the cyclone will be missed. There are miniature cyclones which have been tracked in the recent time with a fury of even hardly about 30-kilometer radius. That's all. So if the SWAT, which is not having that coverage of 100 kilometer, there is an open area within that the 30-kilometer radius cyclone is hiding itself. Two successive satellite passes will not be in a position to cover. So this is only a food for thought. You can very well see there are cases in which even the cyclones have been missed by the same satellite, but other satellites might have covered. So from that time onwards, now we are switching over to 1990s. The tropical rainfall measuring mission TRMM satellites by NASA of Japan. They have the collaboration with the NOAA also. In 1997 it started. It carried a payload of precipitation radar at 13.8 gigahertz and TRMM microwave imager at 85 gigahertz, visible and infrared scanner, lightning image sensor as payloads. Very success story about this one. And thereafter the GPM global precipitation mission satellites started coming in after 2002, and then there is a constellation of satellites, and then currently India is also contributing for that by launching a satellite called Megatropic for that. So TRMM was the forerunner for estimating the precipitation from the spacecraft. Then next jump after precipitation measurement was wind estimation. Over the oceanic area, sea surface area, the surface wind, by surface here we mean about 10 meters above the sea surface. That was planned by a series of satellites by the same NOAA group, NOAA JPL. That name is called a QuickSat. QuickSat. No C is there. QUIK, QuickSat. This is full success story. I will be covering a little portion today, and then tomorrow I will be covering about QuickSat and then what is the limitation, what the problem we faced once a particular satellite had some issues with that. I will be discussing maybe either today or tomorrow. I am not sure where I have put on. And then today's topic only I loaded. Anyway, tomorrow it will come. India also started tributing for estimating the sea surface temperature wind by launching a series of satellites called OceanSat. OceanSat 1 was launched in 1999. OceanSat 2 was in 2009 by Indian Space Research Organization, ISRO. It carried KU band spectrometer, ocean color monitor sensor at 610 to 630 nanometers, radio occultation sounder for atmospheric studies. The defense satellite meteorological program in between I skipped over, probably the continuity was misplaced because I want to cover this one along with Terra and Aqua. That is the reason I have put over here. It was in mid 60s. It is a continuous ongoing research satellites. Even now also the defense naval group, they are doing so much contribution for the satellite technology. The DMSP satellites of US, it carry a very vital sensor, and then almost all the researchers, they use the data called the SSMI, special sensor microwave images, sometime in 1987, and it has both all-weather imaging capability over land and oceanic area as microwave radiation is insensitive to the cloud. With the advantage gained from the DMSP, some of the sensors used in DMSP that has been taken over and then linked into the Terra and Aqua series of satellites by NASA. It carried advanced microwave scanning radiometer. This name is very familiar to scientific group, especially of the meteorology and oceanography origin. Moderate resolution imaging spectra radiometer. It carried the usual AMSUA of 8 hours and atmospheric infrared sounder AIS. And then this is the current day, which gives very, very fine resolution atmospheric profile AIS, atmospheric IR sounder. In addition, it carried a humidity sensor. By name, it was called HIRS. Humidity sensor of Brazil, HSB. So the AIS atmospheric IR sounder, it has different channels that have been listed over here. What are all the specific gases which are usable, and then what are the wavelengths? And here the wave number has been given, not the wavelength. What is the precision, and then what is the degree of freedom? And we have seen so much amount of trace gases in yesterday's module, and then each trace gas is susceptible to some of the radiation wavelength that also we have seen yesterday. There are still trace gases available for which the wavelengths have been identified. We are yet to use those particular things. So they have been listed in the last portion of this particular table. Right now, it is ongoing. Maybe for emissivity estimation, some other thing is on its way. So we have to wait and see. Then National Polar Orbiting Operational Environment Satellite System, NPOESS, way back in 2013. Conical microwave image sounder has launched, and then it carried whatever the Aqua was carrying as an image sensor and then sounder sensor. As I told you, DMSP was the origin, and all those pairs were tried on experimental basis or R&D basis that have been put into operational use. This has a variety of application, all weather SST, precipitation, liquid water of the clouds, snow water equivalent, snow water dissemination or deciphering. Then, as usual, vertical temperature and moisture profile. The ongoing future as well as ongoing satellites of polar orbiting. So far, we are discussing only on polar orbiting satellites that orbit from pole to pole at a low Earth orbit. Okay, low LEO also we used to say. It's a low Earth orbit satellite or polar orbited satellites equivocally. Fengyun of China, they started launching right from 2008. Microwave image radiation image at WI, it was at 6 frequency points. You can very well see the clarity of the cyclone on the left hand side. Very crisp land seawater delineation, the green color and then the dark color separating over here. that can be very nicely identified. The cyclone I is clearly seen. The wall cloud is very much seen. Streamers and feeder bands, they are very nicely located. I think one point I have skipped over here. Let's see. The Messi I have not discussed. It is the improved version of what we call a spectral imager. So with that only this started. I missed it. Sorry. Then in addition, the ozone mapping spectrometer TOMS, whatever was available in number 7. So in that particular concept, so much amount of what we call improvement has come, and the current day in NASA-based ozone mapping instrumentation (OMI), that mission is ongoing, and total ozone mapper on Pyongyang, ozone profiler TOMOP. So they are with Pyongyang, and the current day the ozone, because sometime back the entire world community was alarming over the ozone hole. We want to have the ozone to be extracted. Otherwise, we are having very, very minimum ozone stations or surface. In India, we had only 5, and it may number somewhere around some 38 and 40. That's up. So now with the ozone mapping, etc., once it started coming in, the ozone hole problem, and then the ozone, how it is going to cause the what you call the climatic variability, climate change concept, and then global warming concept, etc., that will be having a say. And then current day, the ozone sounders are on board. So now from VHRR, we have gone to AVHRR. Now that AVHRR is getting replaced by VIRS, Visible Infrared Imaging Radiometer Suite. Earlier, we started with the 2 channels of imaging, then 5 channels, then 6 and 7. Now, empty numbers are coming in depending on the narrow band through which we'll be identifying which channel will be used for what deciphering, etc. So it's a suite. Then higher spatial resolution nowadays, because of the satellites having the improved technology thanks to technological advancement. Earlier sensors were having kilometer resolution, and then the current day sensors are few hundreds of meter, few tens of meter on cartography. Okay, in our case, meteorological application case, few hundreds of meter. That is more than sufficient as of now we can think of. Then the current day technology satellites, they have the capability of measuring accurately SST, sea surface temperature, aerosol, optical depth, snow cover, cloud cover, surface albedo, then vegetation index, NDVI we used to call later on, maybe in image interpretation I'll be in a position to cover that also. Sea ice, ocean color monitoring, etc. And the HIRS sounders are replaced by cross-track infrared sounder series. It replaces the AMSU by using advanced technology of microwave sounder. It's again a suite. And we want to have the temperature profile at 1 degree accuracy at 1 kilometer over the tropospheric layers, and humidity in 2 kilometer layer and 20% of excess. Then in the same polar orbiting satellite, there is another development by ESA, European Space Agency. That name is called as Meteorological Operational Satellite. It carries a fantastic instrumentation called IASI, Infrared Atmospheric Sounding Interferometer, GRASS, Advanced Scatterometer ASCAT. So this is the wind sensor. GOM, which is the ozone mapping. That's what I was saying. The GOM, the ozone detection is going in a big way nowadays. And the timing has been decided. The series and the ATMS sensors will fly on the afternoon ascending path, and then IRC, AMSU, MHSS start flying on the morning satellite, the descending satellites. So the current, with this, probably I am ending up the polar orbiting, then I will take over to geostationary. are all the agencies and then what are all the satellites lines that have been put over in this table. I need not explain, it is viewable. Now I am taking you to a geostationary satellite. The satellite which orbits at the same angular velocity as that of Earth is geosynchronous orbit, and geosynchronous orbit having zero eccentricity and zero inclination is geostationary. So that is the definition, rigorous definition for geostationary. It remains practically stationary above the Earth's surface wherever it is launched over the equator at a particular longitude. But here again, there is a small aberration which we used to call as drifting. That drifting takes place, and then we have the method of correction. The drifting correction is being applied. We are able to see the same view, maybe not much difference, hardly a few kilometers alone that matters, that's all. So that also is getting corrected nowadays. It has the same orbital period as that of Earth, that is 24 hours. How it evolved, the way in which we saw the polar orbiter, now the evolution I am discussing. It started with a communication testbed satellite called the ATS, Application of Technology Satellite, which was launched sometime in 1966. It was having a spin scan cloud camera, that is a bit on camera, we see the silhouette of that. And it was having a full disk image view, whatever the globe it can cover at every 20 minutes. That was a great rate at the time it was considered. It was put into operation setup in 1970s, and 1974 onwards, the sensor technology, then transmission technology like weather facsimile, through which the satellite images as well as the conventional chart, which will be uplinked from the ground to the satellite, and then from the satellite, whatever be the country, whether they have the capability to receive through by means of receiver, if they are not in a position to have their own chart plotted or something like that, or the analysis capability, if they are not having it, the member countries or the countries can download, and then the big fact charts was in operation in 1980s. Then US started its series called the Geostationary Operational Environmental Satellite Series, which we used to call as GOS, GOES. European Space Agency started a series called the Meteosat. The resolution started coming in earlier, 4 kilometer was there, now it has been brought out to 2.5 kilometer, and IR and water vapor in 5 kilometer resolution, upper tropospheric humidity and the clouds. Very nice detection from this series. GAUS and Meteosat, they contributed for the WMOS program called GARP, Global Atmospheric Research Program, which started in 1979. It carried the first vertical profile sounder, that is atmospheric sounder, VSSR, atmospheric sounder in GAUS series of satellite in 1980 September. But somehow or other, due to technical difficulty, it was not continued, and there are so many other things are there. So now the geostationary satellite has furthermore application, especially the stability and instability. We can work out based on the temperature sound in retrieval, which is useful for the operational forecaster to use as a tool for forecasting. The first clarity information from GOES 11 that has been displayed over this particular slide. And you can see the bright white spot, dull white spot, gray spots, and the moment it was identified by the operational meteorologist, then the geostationary meteorological program, both in regard to imager and sensor, it got up very, very fast speed. A classical picture of Cyclone Dennis or Florida Panhandle. As viewed by geostationary. Right now, due to paucity of space in this particular slide, only those satellites which are familiar at that time that has been put, and then probably furthermore satellites are still yet to be plotted over this particular V graph. And Indian location was shown over here as 83. We have 74, 84, 93, etc. So locations, and the similar way all satellites we have missions over this particular view graph. Then the Indian satellite program started. It is a by name called INSAT, Indian National Satellite. It is a multi-purpose satellite for telecommunication, broadcasting, and meteorology. And for broadcasting, it is a TV and visual media communication. Telecommunication, it is a land-based usual telephone communication. In the meteorology, it was threefold. One is the data collection platform. The remote area, the sensors will be collecting and then applying at a particular window time in every hour to the satellite. From that satellite, it will be downlinked to a ground-based receiver, and then thereby the remote places will be having observation, which is similar to today's technology called automatic weather stations. Then the cyclone warning dissemination system, which is a one-way communication, which was thought maybe first time in the geostationary type of what we call era in India. The cyclone warning can be disseminated from the cyclone forecasting officers to the administrators for evacuating the people over the coastline, low-lying area, so that their life and properties to that extent can be saved. So it is a one-way communication. So we had a payload initially when it was launched. Then there is another communication type, that is VSAT, very small aperture terminal, which has a very, very low speed, maybe 256 kbps, 64 kbps, only that order, if I am right. In 1980s, where the internet technology was not that evolved, the mobile technology was not at all in vogue. So communicating to the remote place, so this was considered as the best tool. So the VSAT was conceived by INSAT series. So the sequence and series of INSAT that has been tabulated over here. To mark the respect of Kalpana, we have coined our name, the series name, as Kalpana also. So they have been tabulated here. A classic picture of INSAT detected tropical cyclone in 1991, which is almost a super cyclone, T6.5. All the features, right from streamers, the feeder bands, high wall clouds. Sometimes, two wall clouds are seen. Usually, cyclone is having only one wall cloud very close to the eye. We have seen two wall cloud region, even in one case, three wall cloud regions. So, thanks to the satellite observation, we are in a position to understand the fury of cyclone, so that the forecasting and warning can be improved, and then we have gone to that extent. The same satellite with a color enhancement technique. Here also the same eye is seen. Only thing, somebody will be liking the black and white, somebody will be liking the color technology, but nowadays color technology has gone farther beyond. As I told you, in the left hand side, I have given the symbol as the T6.5, and then the right hand side is 1999 cyclone. The intensity is somewhat lower. The tropical cyclone intensity number is 5.5. So the clarity on the left hand side, clarity on the right hand side, that we have to see depending on the application we are supposed to use. And the current day INSAT 3D and then 3D repeat, 3DR imager, they carry 6 payloads on the imager. The purpose have been listed over here. The sounders, there are 19 channels. One invisible, the last one. Similar to HIRS, the last one, 20th channel here, 19. Now our program, we started a humble beginning long back, and then we have come a far way. We are also contributing the global community by providing the satellite pictures and then satellite data, so that weather does not carry in political country, weather does not mean political country, data is accessible, and then this is useful for the operational forecaster, especially for the international air navigation purposes or the ship navigation purposes. The satellite gives a vital tool, and then ISRO is also contributing. India and the agency is called as ISRO, contributing the OceanSat wind, satellite derived winds, they are playing a vital role. So this is the view graph. So the existing and future geostationary satellites, the NASA group, Xiaomi and PP, that's again the US group, INSAT. This is their view graph 2002 to 2020, what they are going to do by the next year or so. So the launch locations have been tabulated over here. Geostationary is always over the equator or a particular longitude. That's what I was saying. The last column says the launch location. Meteor's second generation says already ongoing, but still improvement is going on. GOES program is also ongoing. Whatever I listed over here, further improvement is always possible. And Japanese Himawari, that the series is going on. So with this, let me complete today's module on evolution of satellite, both operational and R&D. I used my own material, the published material available on journals, books, internet, etc. that I acknowledged. A small reference has been given over here, but today's internet age, the references are plenty. So you can search through any other search engine, and then you will be in a position to get much more idea than what I could cover in the last 1 hour.